A mysterious force, more unknown than known. Dark energy accounts for roughly 70% of total energy in the universe, and we know almost nothing about it. Scientists are still struggling to understand this enigmatic force, which seems to be pushing our universe apart at an accelerating rate. Black holes are dense points in space that create deep gravity sinks. Beyond a certain point, not even light can escape the gravitational pull of a black hole. They consume surrounding matter, grow in size, and eventually swallow entire galaxies. Recently, researchers came up with a new theory, and interestingly, that theory explains a new phenomenon, but it adds more to the mystery too. It sheds light on the connection between black holes and dark energy. But what could this mean? Are black holes the source of dark energy? And where are these black holes getting the mass or energy to grow now? And most importantly, how do black holes form in the first place? Let's find out. Before we dive into this recent groundbreaking research, let's first understand what dark energy is. Our universe started in a very hot and dense state called the Big Bang about 13.8 billion years ago. The universe expanded as a result of this event, and it has continued to expand ever since. But since all the stars and galaxies within the universe have a gravitational attraction, it was thought that this would eventually cause the expansion to slow down. That's what we thought, but in the late 1990s, two independent teams of researchers found that the universe was not slowing down at all, but was actually speeding up. The expansion was accelerating for unknown reasons. The best theory that we have is that there is some unknown energy in space called dark energy. It pervades all of space, acting as an anti-gravity force or negative pressure, pushing things apart. We've since discovered that this energy constitutes more than 2/3, or roughly 70%, of the total energy of the universe. All visible matter that we can see, including humanity, the Earth, and the stars and the galaxies, account for nearly 5% of the total. The remaining 25% or so is made up of dark matter. Dark energy behaves as if it were a type of energy inherent in space. As a result, rather than diluting as space expands, as matter or radiation do, it increases as the volume of space expands. However, this phenomenon remains largely unexplained. This is where the groundbreaking research published in February of 2023 comes into play. In this paper, a group of scientists linked the mysterious dark energy to another somewhat mysterious object, black holes. The overall claim is that black holes, specifically supermassive black holes, couple to the expansion of the universe on the largest cosmic scales, and that the specific way in which they must couple could potentially explain some, if not all, of the dark energy we observe. Before we get into the specifics of the study, let's first understand black holes and how they form. We don't know much about black holes, but Carl Schwarzschild predicted them theoretically based on some of the first solutions to Einstein's equations. Black holes form after a massive star runs out of fuel, sometimes resulting from a supernova. When a star runs out of fuel to burn, it can no longer support its mass and it collapses. This collapse frequently produces extremely dense objects known as white dwarfs or neutron stars. When our sun runs out of fuel, it will collapse into a white dwarf in about 5 billion years. However, if the star's mass is large enough, at least 3 times that of our sun, it will continue to collapse theoretically into an infinitely small object with a finite mass, but infinite density, known as a singularity. The gravitational pull of this object is so strong that nothing, not even light, can escape. That's why it looks black, and it's called a black hole. In addition, black holes can grow by merging with other black holes. However, if there is nothing nearby, then there's nothing to eat. So we can expect them to stop growing after they have consumed everything in their path. A group of scientists decided to look into it further. They studied so-called dormant galaxies that contained supermassive black holes. These are very old black holes that have accreted the majority of the nearby mass and are no longer active. The astonishing discovery is that supermassive black holes in galaxies appear to grow 7 to 20 times their own mass over a period of 9 billion years, which we would not expect. So the question is, where do these black holes get their mass or energy to grow? What do they eat? This is where dark energy enters the picture, as scientists propose that black holes have a connection to dark energy and grow as a result of it. Dark energy may, in fact, be contained within black holes. This also raises a simple question. How did researchers measure these black holes across billions of years? They made the simple assumption that such dormant galaxies would all behave similarly over their lifetime. So by examining similar galaxies at different stages of their lives throughout the universe, we should be able to see a pattern in how they all grow. Because light moves at a constant speed, they were able to see galaxies over 9 billion years. This means that the further away we look, the further back in time that we can see. Because light takes longer to reach us as we get further away, this allows us to look far out into space, back to around 9 billion years ago, and then look at similar sets of galaxies closer to us to see the progression of the growth of their supermassive black holes at the center. Astronomers determine the mass of these supermassive black holes by observing a link between the mass of a supermassive black hole and the mass of the galaxy's spheroidal component, the bulge. There is also a connection between the motion of stars in a galaxy's bulge and the mass of the galaxy's supermassive black hole at its center. Researchers calculate the growth rate of the black holes by observing their mass over time. So now let's look at how this growth in black holes is connected to dark energy. They present a model in which they assume some kind of K coupling between black holes and dark energy. In very simple terms, if the evolution of dark energy growth matches the evolution of supermassive black hole mass growth, you could hypothesize that there must be some connection, depending on how strong the correlation is. In practice, this means that there is no connection between dark energy and black holes if K equals 0. But if K equals 3, the match is perfect. Well, surprise! The result shows that K equals 3.11 plus or minus 1.1 with 90% confidence. As a result, the outcome is full of ambiguity. They also demonstrated that K is not 0 with a 99.98% certainty, implying that there is a very unlikely correlation. If this finding is correct, it implies that black holes may contain dark energy. That is where it resides, whatever it may be. If it is correct, it may also resolve another major issue, the singularity problem. A singularity is a physically undefined point in space at the center of a black hole. This suggests that there is a flaw in general relativity theory, which is most likely correct. Black holes are extremely dense and heavy objects curve space-time. This singularity math appears to imply that the gravity in the center of a black hole is so strong that the curvature becomes infinite. It, in a sense, punches a hole in space-time. However, dark energy is similar to anti-gravity. If black holes are indeed full of dark energy, then this anti-gravity effect may bring a correlation to this model. If black holes are indeed full of dark energy, then this anti-gravity effect may bring a correlation to this model, removing the singularity and resolving the mathematical model's infinities problem. However, if dark energy does exist inside black holes, it is inherently difficult to study because we do not have access to the inside of black holes. We only have a general relativity to explain gravity at large scales, and the standard model to explain the other three forces at small scale. But these two models do not fit together, so gravity at quantum scales remains a mystery. We hope you enjoyed this video. Make sure to subscribe, like the video, and watch these ones as well.